And I forget who gave me this this calculation on back on the 22nd, but thank you for that. And I think that's it for day 22. We should take a look at day 23. Yeah. Let's go right over here and dive right in. Day 23 amphipods. Amphipod. Okay. A group of amphipods notice your fancy submarine and flag you down. With such an impressive shell, one amphipod says, surely you can help us with a question that has stumped our best scientists. They go on to explain that a group of timid, stubborn amphipods live in a nearby burrow. 4 types of amphipods live there: amber, bronze, copper, and desert. A, B, C, and D. They live in a burrow that consists of a hallway and 4 side rooms. Side rooms are initially full of amphipods and the hallway is initially empty. They give you a diagram of the situation. Okay. Amphipods would like a method to organize every amphipod into side rooms so that each side room contains 1 type of amphipod and the types are sorted A through D going left to right like this. Alright. Amphipods can move up, down, left, or right so long as they are moving onto an unoccupied open space. Each type of amphipod requires a different amount of energy to move 1 step. Amber requires 1, bronze requires 10, copper requires 100, and desert ones require 1,000. The amphipods would like you to find a way to organize the amphipods that requires the least total energy. Alright, so is this just Dijkstra all over again? However, because they are timid and stubborn, the amphipods have extra rules. Aha! So this is where it breaks down, right? Amphipods will never stop on the space immediately outside a room. They can move on into that space so long as they immediately continue moving. Specifically, this refers to the 4 open spaces in the hallway that are directly above the amphipod's starting position. So this space here and here, I assume, if I'm reading correctly. Amphipods will never move from the hallway into a room unless that room is their destination room and that room contains no amphipods which do not also have that room as their own destination. Okay. If an amphipod's starting room is not its destination room, it can stay in that room until it leaves the room. And once an amphipod stops moving in the hallway, it will stay in that spot until it can move into a room. Oh, okay. So I think that makes things easier, right? Because then you just need to create for the, I'm still thinking Dijkstra, but what we can do is for the neighbors, we can look through all the hallway amphipods and say, can they be moved into their final location? And if not, then they don't go. And for any amphipod that's in a room it doesn't want to be in, we just say, is there a spot in the hallway for it that's not directly above another room? We don't have to go looking. Okay. Yeah, I think that makes things easier. In the above example, no, not this example. This example. Here we go. The amphipods can be organized using a minimum of 1, 2, 5, 2, 1 energy. One way to do this is shown below. Chunk, 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 chunk. Okay, so I can see they're moving into the hallway and they're moving into the rooms. What is the least energy required to organize the amphipod? So how big is this actual room hallway? Oh. Oh. Okay. So it's the same size. That's interesting. So let's save this as our input for day 23. Let's move it into location. Oh, I never pushed. There we go. All right, so how do we want to model this? Well, first we're going to do is set up our runner. And actually, what am I going to do here? I'm going to modify this so that while I'm developing this, I can actually get this to just run the day I want to run. It is month 12. I don't want to do a run all. I'm just going to say run the 23rd. So I'm just going to say, just temporarily here, which day is 23rd, which is 22 in the index. Right, this fails. Make dir source date 23. Edit source date 23 mod.rs. Okay, and see if that checks. And did I get the run correct? Nope. Run is 23, but the index is 27. Oops, I must have changed the wrong thing. Oh, yeah. Okay, so I want to actually put that here. Which day is 22? There. Now can I run it? Yes. Okay, so this is the temporary hack to just get that to work. Very good. All right, so again, how do we want to model this? Source day 23 mod. What we can do, so I want to, if I'm doing Dijkstra, then I want to create a little a thing that we can store the state in. And then we can just generate neighbors with those additional states. And that's going to be, it's going to be annoying to try to come up with the neighbors, but let's figure that out. Can we just store this as, because I want to be able to, yeah, if I say type room, and the room, let's say rooms, and it's just going to be an array, a two-dimensional array. And what are we storing in here? We're going to store the amphipods. And how do we want to indicate what the amphipods are? We could say, you know, A, B, C, or D, and then map. Yeah, why don't we do that? Enum amphipod A, B. My finger kept hitting the space bar. And we can just say amphipod. And each room has 2 amphipods. And there are 4 rooms. And then hallway is just going to be... Oh, yeah, we want to be able to store a nothing as well. Empty. Right, and then we're just going to have a hallway. How big is this? This is 2, 4, 6, 8, 10, 11. And then our state, I can just make that a tuple of rooms and a hallway. Do I put a semicolon there or no? I do. Okay. So let's see if we can just create just this by hand. So I can just say let our rooms equals, how do we want to define this? This is going to be a BA, a CD, a BC, and a DA. And then let H, hallway, is going to be just empties. And there's going to be 11 of them. Can I do it that way? Oh, I'm just going to use. Hopefully there's not going to be any overloading with the single letters. Oh, okay. I didn't realize that needed a copy. And if you derive copy, you need to derive clone. Okay, so that works. You can define, you can create a amphipod burrow this way. So the state of any particular burrow, let S equal state equals state of R and H. Does that check? That checks. Okay, so we can do it this way. The only question is how do we generate the neighbors' states, right? If we're going to do Dijkstra, we can. I mean, let's throw together a quick Dijkstra. For Dijkstra, we need a Q set, right? That's going to be a state and the cost. I-64. Right. Let's see, use standard collections, hash map. Let's see, and then we also need a dist. First Dijkstra. Right, and then we need our starting state, which is this for now. We're going to just use this test input. We're going to say qset insert S, and cost is 0. And then, oops, 0. I don't know why that didn't come out. And then while qset is empty, what was it? We need to find smallest. And then after that, we do for each neighbor, which is going to be the hard part. If smallest is greater than, then we have to calculate the cost, or no, we have the cost in there already, right? So smallest is greater than the cost, then we say smallest is equal to smallest is equal to the cost. Oh no, it's that alt thing, right? We say alt is equal to the smallest plus neighbor dot cost. Cost was the second value in there. Neighbor dot one, and then this is where we say if alt is less than. This is where we say dist of state S. Then dist insert neighbor dot 0, which is the new state, and the cost. And we also, because we don't have all of the nodes in Dijkstra, we have to actually insert it also here in the qset a bar. I'm just doing it in pseudocode now so that I know how to do it. And then the other part of Dijkstra was doing the previous, but we don't need to do that unless we're trying to do debugging. So the smallest is, I know you're supposed to use a binary heap, but I haven't learned how to do that yet. So this is just, for each entry in qset. If smallest is greater than, we'll set the smallest equals max, smallest is greater than qset 1, then smallest equals qset 1, and found is equal to qset 0. Qset 0. right? And then we're going to check end condition, which means if found is equal to end, then we're going to print smallest. Okay, so I think that's the gist of it for Dijkstra. So we need a bunch of different things on state. We need to be able to calculate the neighbors. For any given state, we need to be able to figure out what the who the neighbors are. I'll put that back over here. There we go. And in terms of cost, so each one will have a cost. What are we going to return for the neighbors is just a list of states and costs. So let me just implement that. NEIGHBR of self. Is going to return a vector of state of. We want to be able to push, yeah, so let's return a tuple of state and cost. And we're just using I64 to represent cost. Oops, this should be an open brace, close brace, there we go. So we're going to need a result. New, and then we'll just return result at the end. Okay, so that's the framework for this. Now what we want to do is we want to say what steps can we take from, let's say, let's start by going from room to hallway. So let's grab the rooms. Room and hall is equal to self.0 and self.1. Did that check? Does not. Oh, it doesn't satisfy EQ. Okay, we can do that. And it doesn't satisfy. Oh, it doesn't satisfy hash. So we have to be able to hash them too. That makes sense. Still no EQ. Oh, do I just have to throw EQ on there? Oh, and now I can't do... So I have to add partial equal to these guys too. Oh, we can't derive that? Why can't we do... Yeah. So what was the error? You can't do equal and not equal on these guys. What if I put them directly in there? I mean, would that work? Oops. What do I do? Yank to the end and put it here. Yeah. And then yank to the end and put it here. Not hitting letter P. There we go. Okay, I can't pronounce that, but thank you for the follow. I'll just say Mondal. Mondal, thank you for the follow. I appreciate that. All right, so if I get rid of this and this. Nixflix, thank you for the follow. All right, so can I do this now? It still doesn't like it. Binary operation equal equal cannot be applied to. All right, so there should be some way of doing this. And it's for both of them. It just keeps repeating over and over again. Oh, because it can't derive partial equal or hash. All right. So what's the right approach here then? Oh, is it because of this? Do I need to add this here? Oh, okay. So that was the problem. All right. So let me put the room and hallway back because I like those. Room type room equals this, and then type hallway equals that, and then delete that, and this goes here. Can I do that? I can, and then I want to make this rooms and hallway. I'll change this to rooms and hallway. Change this to rooms. All right, so that checks too. All right, thank goodness. So that was the problem. It was complaining down here, and I was very confused because I thought maybe this needed to be it, but it was really the amphipod that was missing the thing. So I was misreading the error message. All right, so we're able to destructure this guy here and get the room and the hallway out of it. So now we're going to loop over each room, and the room is a So each room is going to be, let's grab the index too. So I and amps, the amphipods. Let's say instead of I, let's say column. So C for column. In room dot enumerate. And then we're going to say the column it's in is going to be, let's say, if we start numbering this at 0, 1, so this is 2, 4, 6, and 8. So it's just 2 plus C times 2. Right, is the column number that we're going to go for. And then, we need to calculate, can I do an impl on the enum? I know types you can't do an impl on, but maybe impl amphipod? I can't spell this. AMPHIPOD. And costs. Self. And it's going to return, what am I using? I64s for costs. Match self. A is 1, B is 10, C is 100, and D is 1,000. And then we also want to say col. For what column do they want to go to? And that's going to be U size. Match self. Oh, and an empty. We shouldn't ever ask for the cost of an empty column. So let's panic if we do that. No cost for a non-amphipod. There. And this will be, what column do we want to go to? A wants to go to column 2. B is 4. C is 6. And D is 8. And Then empty is panic. No column for a non-amphipod. Oh, and then semicolon. I keep making that mistake. Okay. So this should check, hopefully. Oh, arrow. There we go. Cannot be called on... Oh, iter. Okay. So that checks out. So now I can actually say... oops, I just dropped my phone. What is the desired... Which column do we want to go to? Well, first of all, we want to make sure that we actually have... It's not empty. So we're going to do... We're basically doing this as... this is 0 and 1. Right? We have B and then A. So 0 and 1. If we loop over them, it's kind of a silly thing to loop, but we can do it. 0 to 2. The amphipod, I guess, in 0 to 2. We want to say if amps of A is empty, continue. Because what we're doing is we're trying to generate right now. Oops, let's go down here. Come up with a list of moves for amphipods leaving a room and going into a hallway. So if it's empty, then this, else we want to find out which column the amphipod wants to go to. So let desired equals amps a dot call. Right? Is that what I called it? Call? Yeah, call. So if we're already in the column we want to be in, then we don't need to go anywhere. Oh, that's not entirely true. Right? Because if we have, let's say these are reversed, where we have C on top and B underneath, we need to move C out. So C can only be there if C will want to move out if it has a non-like amphipod in its desired column. So if A is 0, in other words, we're on the top, and we're in our desired column, and the guy underneath us is the same as us, then we can continue. We don't have anything to find. If we're on the bottom column, or if we're bottom of the column, and we're in our desired location, then we're done. We don't have to move out. So now we want to say, is there a spot in the hallway we can move to? And we only move to certain spots in the hallway, right? So 0, 1, 3, 5, 7, 9, and 10. I think that's it. So we can just loop over that for hallway position in 0, 1, 3, what did I say? 3, 5, 7, 9, and 10. Right, 0, 1 of those, and then 3, 5, 7, 9 are the ones that are above the thing to the right, and then 10 is that last guy over there, right? Yeah. Okay. I think that's right. So if, and we grab the hall here, of H is not equal to empty, right, what we're doing is we're moving along here. Oh, we need to be able to stop. So if we're going to move to the left, we want to keep looking, even if there's a non-empty, like this D guy. If we spot an amphipod here, we want to keep looking forward. But if this, let's say we're looking for this C guy to move out, and there's an amphipod right here above this spot here, right? Once we hit that, we want to stop looking, because we can't go any further than it. But if we're coming from this direction, we do want to keep looking. So we need actually a second vector that we can fill in for possible locations. So if we're working from the front, if H is less than our desired call, no, if H is less than our current column, which means we're to the left of this guy, then all we do is say possible clear. So any spots we found already, we're going to just clear those out. And what we'll do is we'll extend our result with possible. If H is greater than call, which it should be, then we're done. We have no more things to look for. So we can just do a break out of this H for H loop. Right, so then we're going to do a similar check here. If we're looking in the top column, if we're going into the top column, or we're going to go into the bottom column and the top column is empty, top of the column is empty, then we can go into this guy. Right? I'm trying to mentally model it. It's there, but so we're going to just push in the hallway that we're going to come from and the column, or the spot in the column we're going to go to. We'll just push that into the vector. That's it. All right, so if we can move to where we want to go. Sorry. If we're coming from the top or the bottom and the top is empty. Right. I was thinking one step ahead where we're going from the hallway into the room, but this is coming out of the room into the hallway. So we want to say, if we're on the top, or if we're on the bottom and the top is empty, then we can come from this location. And then after we've run through that loop, we want to generate now a new state in our result vector with that description. So we're going to loop over all the ones we found, and now we're going to create a clone of the room. We're going to create a clone of the hallway, new hall. All that clone. And then we're going to say new hall, and p.0, which is our hall, is it going to equal to new room of the C, the index we're in, which, the column we're in, and it's going to be whatever's in p.1. Right, we're going to move out from this, which is p1, into this. And then the room is going to get cleared. And then we're going to push that as a result. Oh, and then we have to calculate the cost. And so, okay, so that cost, and it's going to be P dot, oh, okay, before we do that, we have new room CP dot 1 cost, and we're going to multiply that. Oh, you can just say that's the cost, and just push a new state with new room, new hall, and this is a tuple, so we have to do this, comma, and now our cost times how much we're moving by. So we're moving by P1.1, which is our starting location, right? It's going to either be 0 or 1, so we want to add 1 to that. So it's 1 or 2. So we're either moving 1 out or 2 out. And then we want to move the distance to, we're either moving left or right, so we need to do an absolute value calculation here of col, which is where we are, minus where we want to go, which is h, abs. Oh, that fits on one line. Okay. That's a little nutty. Does this check? It doesn't check. Okay, we can't break here. Oh, else if. What else? Oh, possibles not found in the scope. Oh yeah, this has to be, that makes sense. This has to be here. Because once we've generated all the possibles, we can do it here. That was bad. Supplied 1 argument, expected 2 arguments. Like that. No? No method abs found for type use. Oh, shoot. Okay, we're going to have to fix that then. Because you can't subtract and get negative with a U size. Okay. This, I don't understand this one though, because I'm creating a... Oh, it's a tuple directly. It's not a one pole. Okay, so let's fix now the abs thing. So we're going to have to say let start I64 equals call as I64. Let end is going to be P dot I64 is to P dot 0 as I64. And we'll just say start minus end here. Oh, it still doesn't like it. Oh, we can't add it to a U size. Okay, now we're going to go longer than 100 columns. So as U size. Oh, that should have worked. Expected I64. Oh, okay. So this is as U size, and then this final thing is as I64. Nope. Oh, that's there. Okay. Like this? Yeah. All right. Okay, what else? So this is the list of moves for leaving a room. So now we need to come up with a list of moves for entering a room. So how are we going to do that? For hallway into room. So what we need to do is look in the hallway and see what's available to move. So we can just say for, we'll just do C and amp again. In Hall enumerate. Right, that's what we did up above, right? We just looped over the room. Oh, iter. Yeah. So now we're going to do something similar, but we're going to say, okay, if, but now instead of this being multiple, right? This is not, this was 2, right? It was an array of 2, but this is now just a single amp. So let's just say amp. Oops. Amp. So if amp is empty, then continue. So if there's nothing in this hallway position, then we don't have to do anything. So now what we're going to do is look for the column that the amphipod wants to go to. So let's use desired again. This is amp dot col. So now if where it wants to be is less than where we're looking now, yeah, so this in this case, I was just thinking, in this case we had to translate the C into an actual column because we have 0, 1, 2, 3. But here we just have 0 through 10. So this is correct. We don't have to translate this C into a call. So if we're less than, right? So if we're back here and we want to go this way, then we need to check every spot along the way to make sure there's no other amphipod in the way. So we can say for H in desired to C. To equal C? No, just to C, because C we know there is an amphipod there, and that's the amphipod that wants to move. So we only want to check up to one before it. If I have to be able to break out of this. Because I want to say if Hall of H is not equal to empty. So we found another amphipod in our way. We want to break, but we want to break to next, and we'll just call this guy next up here. Right? Because if I just said a break by itself, it would break out of this form, and we don't want that. We just want to stop altogether. Oh, not break next. We want to continue next, because we want to look at the next hallway position. Right. So actually what we can do now is we can say else if desired is greater than C, then we'll do the other way around for H in C plus 1 all the way to our desired column, but this time we actually have to check it. Right, now we want to move forward. We're up here somewhere and we want to check forward to see if there's any amphipods in our way. If Hall H is not equal to empty, then continue next. Okay, so now we're at the point where we can actually check to see if we can move into the room. So now we have to convert. Okay, now we have to convert into a room because we have 0, 1, 2, or 3, and we have a desired column of 2, 4, 6, or 8. So let's say let R equals desired divided by 2. Right, that gets us 1, 2, 3, 4. So now we subtract 1 and we get 0, 1, 2, 3. We have room of R of 0 is empty. Right, that means we can move in. And now we want to see if we have to move to the bottom or if we have to move to the top. So if room R0 is empty and room R1 is empty, then our new room, so we're adding to this result vector. So we need a new state, which has the amphipod moved to that spot, and then the cost of it having moved to that spot. So we're going to do the same thing here. New room is equal to room clone, new hall clone, new room of R and we're going to move down to spot 1 is going to be equal to the amp, right? We called it amp that we're moving in, and new hall of H, well, not H, of C, right? That's the index into the hall is C. H was this thing here, is equal to empty. So that's our new state, and then we say result push, state, new room, new hall. That's our tuple. Oh, that's right. It's not a tuple like that. It's a tuple like that. And this is a tuple of, and then we need our cost again. Let cost equals amp cost. And then we just say cost times, and now we're moving from the hallway we'll do as I64 minus C as I64, right? Because we're moving from this guy to this guy, dot ABS. Oh, and then we need to add on how much it's going to cost to move in. And we're moving down 2, so we just say 2 plus this guy. Else, if room R0 is empty and room R1 is equal to the same type of amphipod that we are, I think that's all we need to do. And then we just do the exact same thing, except it would be nice to make this a little cleaner. We're going to move to a 0 here, and instead of going down 2, we're just going down 1. Does that check? It does not. Oh, I'm going to have to star all these guys, right? These are all going to be except for those. All right, we'll just do it one at a time here. All right, so that checks. We do have 6 warnings, but it's probably dead code. No, I'm calling cost and call. Oh, because I'm never calling this neighbors function. Okay, that makes sense. And I'm not using dist. Okay, yeah. Oh, that's fine. All we're trying to do is come up with the neighbors function right now. Is there anything else? What am I missing from my neighbors function? I'm sure I got something wrong. Okay, so find the smallest. So yeah, let's do the Dijkstra thing now. Let smallest mod. Smallest is I64 max, and then our found guy, just set it to none. So for, let's see, we're going to go through the Q set. So our state and cost in Q set iter. If smallest is greater than our cost, I'm remembering the star this time, then smallest is equal to cost. and found is equal to some s. Do we need to clone it here? Sure, why not? And then, so that's this part here. Check the end condition. Oh, yeah, we should set up the end condition. End condition is going to be E, rooms. It's going to be AA, BB, CC, and DD. All right, and then we'll check. First, we're going to check to see if found is none. Panic could not find solution. Then what we do is check to see. We have to unwrap it. Found equals found unwrap, because I want to just compare it equal. If found equals end, then we found it. So we'll just say print cost equals. Oh, this is day 23 part 1. And it's just smallest. And then we can break. And then now we need to do the neighbors thing. So we're going to say for n in found neighbors. And then we're going to do this part and then close. Does this check? Can't compare state. Uh-oh. Oh. So we have to create an end condition is equal to state of and in H. That's not going to work because I moved this thing here. No. So this is end condition. Okay. Okay, that works. I like that. All right, so if we get to this point now, we have a bunch of neighbors. We're going to calculate our alt is the smallest times, oh no, plus n.1. And then if alt is less than dist.get n.0, and if it doesn't exist, we can just do an unwrap or I64 max. Then we're going to set dist insert n.0.clone with alt and qset insert n.0. I have my phone set up here that I can look at it in case somebody texts me, and then this keeps falling over. Okay. Clone alt. And that's I think that's all of Dijkstra. That's all you need to do for Dijkstra. And that way it inserts a new qset with an alt, and then it'll come back up here and find it, and it'll find all the neighbors, and it'll keep working its way through until it finds the smallest, or until it reaches the end condition. Does that check? It does not check. Oh, let. I forgot the let. Okay. Okay. And we can't clone this. Let's fix that. Copy clone. State cannot be dereferenced. Isn't it? But I had, okay, I'm not going to ask. That's what it said last time. Okay, so let's run this. This is with the test input. And we have an infinite loop. All right, let me come over here. Come over here and kill it. There. Okay. So we messed up. I wonder if we're looping, and we can't be looping here forever, right? Because we come up with, we just enumerate the rooms. And we can't be looping here forever because we enumerate on the hall. So we must be doing too much here. Or it's never finding an end condition. It just keeps going. So let's see. What's the easiest way to do this? If I derive debug for this guy and for this guy, can I just print them out? I just want to print out the first set of neighbors, and then we'll stop after one loop. Oops. Print in n. Let me see if I can print these guys too. Start equals this, and with state, and then final is end condition. That checks. Okay, so I'm just going to do a cargo run here. It did come up with a bunch of moves, so let's see if these moves make sense. I do see these print out here, and then a bunch of empties. So now these are the neighbors, right? And this is a cost 30. So it looked like the first one popped out. The B popped out to go here. Makes sense. That's 10, 20, 30. The B popped out. On this line, the B popped out to here. Okay, so this worked too. It skipped the column above it. And skip the other column, so 20, 40, 60, 80, and 90. So 10, 20, 30, 40, 50, 60, 70, 80, and 90. Okay, so that all worked. So it's coming up with states, and I see the D came out here, and I can see 9,000, 8,000, 6, 4, 2, 2, and 3. Huh. So it looks like it's coming up with at least the first round of neighbors. It might, maybe the hallway, going back into the hallway is not working right. Because I don't have any examples for those. What if I create a test for just moving from the hallway into a room? So that would be just creating a brand new room here and hallway combination, and then we can just get the neighbors for those. So let's do that. Let E equals, no, E. We can do a test room. Rooms equals, and then we're going to create one with an empty A, and then B, B, and then C, C, and then D, D, and then let test hallway is a hallway, and it's going to have empty how many empties? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. I'll put an A all the way at the end there. And then I should be able to say let test state is equal to state of test room and test hallway. Println test state. And then for n in test state neighbors. Not passing anything in, and then we'll just say println test state or neighbor. And then we're going to break. Just exit out of there. Now we got warnings of unreachable code, but that's okay. So let's just run that. Okay, that worked. I said because I thought it would find more than but that makes sense, right? So we have our test state, and it says 7 for our cost. 1. So we start here. We go 1, 2, 3, 4, 5, 6, 7, 8, 9. It should have been 9, but we came up with 7. So there's one bug. Is the cost is a bug, but we were able to get to the end condition, and it did stop looping. Maybe it's just slow, and I just need to run it with release. But let's fix that cost. We have a cost bug here. So I said it's the P1 is what? I've forgotten what P1 is already. P1 is the place we want to go to in the room. Oh no, it's the hallway into the thing is messed up. This should be, so I put the A here, and it should be 1, 2, 3, 4, 5, 6, 7, 8, 9, and it came up with 7. So it's the cost plus. Oh, that's why. I said 2 plus this, but it should be 2 plus this, and then another close paren there. Yeah, and the same thing over here, like that. Okay. So let's run that and make sure the cost is 9 now. It is. Okay, good. So that's that bug. Ooh. So let's comment this out. Oh, comment this out. And then see, let me just try running it release and see if it goes any faster. Or if I really do have an infinite loop in here. Oh, I shouldn't have run it release with all the prints. Or I shouldn't have, yeah. Let me comment these prints out. Is that the only one? Yeah, and I'll get rid of the break. Yeah, no, so it's not finding good states, a good end state. All right, well, let's debug. I wonder if it would make it easier if I created a print for the state so we could actually see it like this. That's something to do, right? While I'm thinking about what my bug could possibly be. Print self. Oh, it doesn't return anything, it just prints. Okay, so what we're going to do is println 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and then the n is 12 and 13. And then we're going to do the first of the hallway, dash n, backslash n, and one more hashtag, and then for h in self hall iter. Match H. It's A, then we print A. B, C, and D, and empty, B, C, D, and dot. These need to be commas. And then after we're done printing the hall, we just say println, or print another one of those, a new line. And now we want to print out the columns, or the rooms. So if I do 1, 2, 3 like that, and then say for A in self room. Oh, it's not self hall, self dot zero, right? It's just a tuple. Yeah. So this is self.1. Okay. Self.0, we're going to do match A. And we do the same thing except stop it. Except we'll put a hash after it. And then, match A of 0. I'm just going to do the top ones because then we're going to say print 2 more of those, a new line, 2 spaces, and a hash. Okay. And then we'll do this again. Copy, paste, and match on A of 1. And then, I forgot the hash here and here. And then after we're done with that, then we want to say println. So we just finished this hash here, so we want to do a new line, 2 spaces, and then 2, 3, 4, like that. I think that's it. Let's try printing those and see how those look. We'll just say s.print and see what that looks like. Smab UK, hi, how are you? Good to see you here. Doesn't like this. Oh, I did this on Amphipod. I want this on state. That was dumb. All right. Let us do, let's go down to impulse state. That's a big one, right? Because of the neighbors thing. And then we'll just delete all this and move it. D, paste. Have you finished, did you do the rest of Advent of Code? All right, let's see if this checks. Okay, that checks, so let's try printing that. Or let's try running that and see if it prints out the initial state. See what it looks like. Oh, look at that. That looks pretty good. BA, CD, BCDA. Okay, perfect. All right, and then we should be able to print the final state as well. And condition. Right. And then what I'll do is I'm going to do this n.print. Oh, n.0.print. So we can take a look at what all those are, and I'll just break after the first round. You finished. Oh, good. I'm happy for you. I'm still, like you can see, I'm on day 23, catching up after going on a short break to go visit family. All right, so that was exciting. So this is our in condition, and then we can see B going there. Okay. So it's printing out nicely. Those are all of our C's. And then the second B works its way around. And then the D's work their way. Okay, so those all work. So there must be something wrong with the way I'm generating the states. We must be doing an infinite loop, visiting states we visited before. Oh, I just saw it. We forgot when you, one of the things in Dijkstra is you remove the thing you found. So we have to do a QSet remove of found. And I missed that. Smab UK says, but 23 and 24, although I modeled everything, I ended up solving the puzzles mostly by hand. Yeah, actually, that's a good point, right? I mean, this is small enough. And I thought that when I saw the puzzle, I thought the input was going to be like these really, it was going to be wide with lots of columns and lots of deep rooms and stuff like that. But no, it's just. So you could definitely do this one at least by hand. I haven't seen 24 yet, but I didn't know Dijkstra. So Smab says, I don't know Dijkstra well enough. I didn't know Dijkstra well enough. I mean, I had implemented back in my university days, but I've done it, now this is the third or fourth time we're doing it in Advent of Code, so it's starting to sink in. Expected state like that. Okay, let's see if this works. Nope, let's not print them out. Yeah. Now this is the test input, so let's see, are we close to getting, what was the answer supposed to be? Oh, here it is. Oh, we got it. That's good news. All right, let's try it with our actual input. Except I don't have a parser, so I'm just going to do it by hand. So the rooms look like this. This is test data, and we'll just put our rooms in as inputs day 23. Oh, input day 23. So it looks like B, C, C, D, A, D, and then B, A. Given data. All right. Did I save that? I don't know if I saved that. Well, we'll run it and then see if it comes up with the same number, and then we'll know if I saved it or not. It is slow. It took 2 seconds in release mode. So I'm not doing it the best way, but let's see if this is the answer. Hey, all right, good. So git add source and input, git commit -m day 23 part 1, push. All right, let's see what part 2 is. Smab says, I almost have 24 solution working computationally, but I'll revisit it in the new year. Yeah, I mean, I'm looking forward to seeing what it is. And what the hell? Oh, you bastard. You absolute bastard. I hard-coded everything. Oh my God. Oh. All right. All right. You bastard. Okay. We can do this. We can do this. Don't give up yet. And Vim. There we go. Yeah. See, I hard-coded that it goes 0 to 1 or 1 to desired for the first part. And for the second part, I did the same thing where we either move in once or move in twice. Thanks. Smab says, welcome to part 2. Thanks. Well, I'm glad nobody spoiled it for me because my reaction would have been slightly different otherwise. Okay, how are we going to do this? How are we going to do this? Do I just copy and paste my code and then just put in a hard code it for 4? There's no part 3, right? Good. Okay. So this isn't going to be too bad, right? So we can just change this to A from 0 to 4. Oh, but that's going to break from my part 1, right? So I can't. But I can do. So I've lost track of what my indices are, but I should be able to do it by index, right? But I can't reuse state then because I've hard coded this here as too deep, and you can't go in on this thing. I can't pass in an n parameter because Rust doesn't allow you to do that because then the type is not known at compile time. I can change it to a vec, a 4-way vec. Okay. Why don't we do that? A 4-way vec of amphipods. And then see what breaks. Everything's going to break. Oh! This field does not implement copy. Why not? Why doesn't that implement copy? It's just a vec. Vec implements copy, doesn't it? Okay. Do I just punt and create a second day, day 23A, and then just hard code everything for 4? Oops. It would probably be quicker. Yeah, it'd probably be quicker. I agree, Smub. Okay. Of course, it's going to break my everything. That's all right. All right, and then we'll just do 23 there. Enter source day 23A. Copy source day 23 to day source day 23A. And then I guess if there's time, I'll not today, but maybe tomorrow. I don't know how tomorrow. Usually the 25th. So tomorrow I'll do 24 and 25. And usually 25 is straightforward because it only has one part. At least in previous years, the first part was solving a slightly easier problem than the previous few days, and then part B was solve all the previous days, which we will have done. All right. So I'm going to change this to 4. 4. And I'm going to change my test data. to this, and then we'll see what breaks. All right, so this is B DDA, and then this is CB, and then this is BA, and then this is AC. DACA. Okay. And now we're going to change this code here to loop to 4. And now we have to check these conditions here. So if, let's just do for check in A to 4. Oh no, we have to go through 0 to 4. And we want to say it's either empty. If it's not empty, if, let's say, amps of check is not equal to empty, then we want to say, is it equal to our type? The type of amphipod we are, which is what? Amp of A, right? And amps A is not equal to amps. Oh, if A equals check. Oh, it'll work. Amps check. Then we're gonna we don't want to continue. We actually want to go to the next room. So we'll do the same thing we did here. Next room. Continue next room. Right? Is that the way we're going to do it? I think so. Yeah. Is that, oops, I missed this. Is this good enough? I think it is, because we only evacuate from the top. So there won't be, I'm thinking, well, what if there's an empty and then an amphipod and then an empty and then another amphipod? We don't need to worry about that condition because we'll never get into that state. We either pop out the top, in which case there's empties, there's no gaps, right? Or we go all the way to the bottom and we fill in from the bottom. So there'll never be gaps. So we're going to check. If it's not empty and it's not ourselves, then we'll just go to the next room and check somewhere else, because we can't go into this room. Right? If we can go into the room, then we want to go into the bottommost location. Which means I'm doing this one step at a time. I don't want to do it this way then. I want to just check from the bottom up. So that means this has to go here. Right? That goes in place of this check. So we want to be able to say, can we, we're leaving a room. Okay. If we're leaving a room, that means we want to make sure all the entries above us are empty. That's what we want to check. So we want to say for check in 0 to A. If it's not empty, then go to the next room. We can't go on. Okay. And when A is 0, that check gets skipped. If A is 1, we check 0. If A is 2, we check 0 and 1, and so on. Okay. This I can buy. Then we do the same logic, but now what we're going to do here, we're checking to see if we're at the top and we're in our desired location and the person and the amphipod below us is our type, then we continue. So here, all we're going to do is check. We're going to check to see. We now know that once we get to this point in the code, we know that above us is empty. We want to check all the amphipods below us. If we're not in the right column, right, then we want to check. Then we want to move. Okay. Okay. I guess the first question is, do we want to move? Well, are we somebody first? Are we a mover? Right? This is what this guy is doing here. All right, so the first thing then what we'll do is, even before we go into here, this is what we'll do, is we will count we're going to say for A in 0.4. Okay, I'm going to do it this way. If amps of A is empty, or amps of A is equal to our desired column. Right? And I'm going to say count plus equals 1. Let count equal 0. And so then after we do that, if count is 4, then we're going to continue. Right? So this is just checking if it's empty or everybody's in the right column. We hit 4 of those, and there's nothing to do for this particular room. So now we're going to check each one of the positions. And we're going to say if room of the column we're in, and then A is empty, there's nothing to do for this particular entry in the room. Let's get rid of that. So we're still going to do this desired thing. So now we know that we know where we want to go. We're going to check the hallway. So let's get rid of all this. We know we can come out, and we're not an empty. So C comma A is not empty, and we can move out. So now we're going to check the hallway. So we do the same thing here. The only difference now is we have to loop over each of the entries above us. All right, you know what? Instead of looping, I'm just gonna be lazy. A is 2, and amps of 0 is empty, and amps of 1 is empty, and or A is 3, and amps of 0 is empty, amps of 1 is empty, and amps of 2 is empty. Right, and then we'll add it to our possible. Ugh, that's yucky. Okay, and now we're going to actually have to change this, right? Because we're moving, we're not just moving up. We are moving from P1. Right, so that should stay the same. So it's 1 plus the distance. Yeah, okay, that stays the same. Okay. And then what do we got for here? What do we need to change? We need to... We can start searching from the bottom up. So if we start from the bottom and we call it the best location to go to would be 3, we can say while best is greater than or equal to, no, not greater than or equal to 0 because it's a U size, so it'll never go less than 0. All right, let's just loop and then we'll say if best is 0, break, and the best minus equals 1. So this will be that'll be our break condition. This is a little sloppy, but it does the trick. And we can grab this and put it here. But we need to modify it now. We're going to use best instead of 0. Right. That's still amp. That still gets set to 0. And then I'm going to multiply the cost by instead of going down 2, we're going to be going down best as I64 plus 1 plus that. And then this comes out. That's kind of sloppy. I actually compiled. Wow. Or cargo checked anyway. Okay. Change that to a 2. Oh, yeah, and we're doing test input. So let's see, what are we supposed to get? Oh, where's the cost? Here, 44169. Oh, I'm not using... Oh, I forgot to call it day 23A. And we're not using next room, it said. That's true. Okay. Oh. Oh, this is the end condition, right? The end condition needs to be updated. Okay. It's just AAAA. And BBBB. And D. Okay. I wonder why. Oh, the cargo check isn't checking because I forgot to set it up. Oh, I got to run it release because it takes too long. And this is going to go even longer because it's a bigger search space. And I'm printing out wrong too, right? I didn't update my print function to handle it. All right. But I'm not going to worry about that if it comes up with the right answer. Yeah, Smeb says looks like the wrong diagram. Yeah, I didn't. Remember, I hard coded it to have 2 lines. Well, either I broke something or it's taking a very long time. I guess I can take a look in another window with smaller text. AOC source day 23A mod. Smab says possibly both. Thanks for the vote of confidence there. Yeah, this is the print function I need to fix for I don't know, depth in 1.3.4, and then this just becomes depth, and then it should print out correctly. All right. I wonder if I'm stuck here. I'm definitely subtracting 1 from best, and best is 0 then break. Take a quick peek. No, it's still running. Yeah, it's got to be infinite looped. All right, let's go back to the larger font size here. All right, and I didn't forget to. I didn't delete the remove. No, I didn't delete the remove. Okay, let's print out. Let's do the same thing we did last time and print out the first set of moves and see if they look reasonable. Cargo run release loss. Oops, I forgot the new lines. All right, let's fix that. And it's got to be new line space hash, I think. And then you don't want to print here then. Okay, let's try that again. Oops, I keep doing that. Okay. We'll get it. We'll get it. This should just be a print. There. Okay, that looks better. All right, so the B comes out. Yes. The C comes out. Yeah. Okay, so those all look reasonable. And then I was going to check moving into a hallway, right? And I had some test line in there already, right? Yeah, this one, but I need to add more to the rooms. So let's see if it comes up with a oh, I keep forgetting I can't do cargo check here. Cargo clean. Now I should be able to do a cargo check. Four warnings. Okay. And that's because I'm not oh, right, now it's got to build the whole thing. The warnings are because I'm exiting too soon. I feel like I'm really close here, though. I probably just forgot one more. Oh, interesting. That's why. It's not putting it there. It should have taken this A from here and shoved it in this slot here for the new state, and it's not. So that's the bug. All right, let's see if we can find that. What did I do? And that would have been coming from the hall. That's this code here, coming from the hallway into the room. That's this. Right? Hopefully that's the bug. All right. Oh, I want to make sure I don't print these things, and I want to make sure I don't break. Save. Archive run release. And this is the test data, so we should be getting, what's the answer? Oh, 44169. Come on, please work. Did I have another case where I used 1 instead of best? No? Yeah, so this checks to see if something. Okay, so and this here, did I mess up something here? 0, 1, and 2, 1, 2, and 3. No, it's still running. Yeah, that, oops, don't print. Go to this thing here. Okay. All right, well, let's take a closer look at the code. Let's go to the larger font. And take a closer look at this code here. All right. So this is saying we're going to look inside each column and see if it's empty or it's where it wants to be, then we increment the count. And if we hit a count of 4, then we're not moving anything out of this particular room. That makes sense. So then we check each column. If the column is empty, we continue. All right, we're going to look down within the column 0, 1, 2, and 3 to see the first non-empty one. Oh, then if we're checking the empty, we don't actually have to check here, right? But that's not the bug. This is just a redundant check. All right, so then we're looking in the hall. If the hall, so this is that same code. That shouldn't be different. All right, we're still checking the hall the same exact way. Right. And then we see if A is 0, then we don't have to check to see the above ones are empty. But again, we don't need to check. We should just be able to say, okay, we've already checked to see all above ones are empty. Therefore, we can just push. So I'm just going to do that. And this probably can be cleaned up here too, but okay. Let's make sure I didn't do anything broken here. So the new hall is getting the P0, which is the H, P.0, is going to be equal to, let's just make sure our cost is correct. Amplified, so whatever's currently in the room, whatever its cost is going to be calculated. We're going to move it from the room to the hallway, and then we're going to clear it out. Right, and then our start and end columns, and then we put in the cost. So that seems right. And when we printed out the examples, those all looked right, although I didn't print out the costs. I'm assuming the costs are correct. All right, so the bug must be here then. We must be coming up with extra moves somehow. All right, so if it's empty, if this hallway's position is empty, then we just keep looking. We figure out where we want to go. So this code is the same. All we're doing is checking to see if we're gonna, if we have a clear hallway. And then this is the place we want to go. And now we're going to check the best location we can find. The lowest, right? The lowest location we can find. If it's empty, if 3 is empty, then we're going to set the room to be that amphipod. We're going to put the amphipod in the room, and then we're going to set the hallway to empty, and then we're going to calculate the cost based on that. This all looks right. This all looks right. All right. Oh, and yeah, when I get to it, I'll update my current data. But right now, I just need to debug. What if I have, for this test data, I'll put 2 empties, and I'll put an A on each side. And we'll just test that out. That should be able to find both moves. Is this where we actually want to store the previous, and then we can see both moves one at a time? While a train comes by, let's do that. Oops. Let mut prev, and prev is going to be, this is the Dijkstra thing again, it's going to be a state to a state. So we'll put that in here. We're just going to say for the last one, prev insert and clone to found clone, and that way we can print it out when we find it. We say found.print. And then the way we back up with Dijkstra is we start off with our current one as U, and then while prev contains key U, we're going to say let V equals prev get U unwrap v.print, and then U is equal to V. And that just works its way back to the beginning. And doesn't like that because dereference the borrow. Okay, I can dereference the borrow. All right, let me try running that. I'm going to put it through less just in case we infinite loop. Okay, it actually we do have a 4. So I see that the first room has 2 empties here, and then it only has 1 empty here. The hallway had an A at the beginning and now no longer has an A, and the A went in at a cost of 4. So 1, 2, 3, 4. That's right. Oh, it's putting it here with an empty here. That's not good. We're not supposed to do that. Okay, I think that's the bug then, and we should never go to the top. We should never go to the top, which means that, where is that code? Here. Once we found a spot, we need to break here. I think that might be the problem. Right? Yeah. I think that might be the problem. But now that I'm thinking about that as being the problem, we also have to make sure that we don't find a room that has the wrong sort of amphipod in, right? We want, if we're putting A in here, we don't want to be going back up this way and seeing a D, for example. So I think that means I have to say if room R best is not equal to the amphipod we are, then break. Let me run this. Actually, for this, let me print out. I can use the print function. TS print. N dot print. N0 print. Yeah. Let's see what that looks like. Okay. So, yeah, I don't know if you remember, but last time we had 4 different solutions, and now we've only got the 2. Right, which is perfect. So I think maybe that, let's see if that's the last bug. All right, so this is we're gonna run our test data again. And I'll leave the prev stuff in there just to see. Oops, I don't need that, go away. Let's run this. And now it's going to print the backtrace if it finishes. We'll give it a minute, because who knows? Maybe it's just really slow. Or maybe there's another bug. There must be yet another bug. All right, killed. Yeah, we're breaking out of this loop, but we're not breaking out of the outer loop, which is checking each hall, which is fine. We want to check each hall one at a time. All right. Well, let's print out. And it's frustrating that it's just looping infinitely. I'm going to print out a few of them and then just take a look to see if. Yeah, I think the problem with just printing out a bunch of them is I don't know what the from is, so I'll have to do that. I'll have to print that out. So we're going to just say println from. Let's put a new line from, and I'll just say found.print. So we'll get a lot of duplicate output, but okay, whatever. And then we'll just take a look at some of the output and see. I have not yet found the problems, Matt. Sorry. We'll get there though. All right, so if we're going from this, we can get these. Let's look for from. And see. Oh, okay. I found another problem. It's pulling things out of non-empty, right? It shouldn't have been able to pull that A out through the D. But I thought I was checking up here. Wasn't I checking to see if they're all empty? It's either empty or the right amphipod. And this is saying if it's empty, then continue. So, okay, so I do, if it's not empty, then it's, okay, so I do need to check above for, let's say, I can't use C for check, I used check last time, right? Check in 0 dot dot A. If amph of, no, room C of check is not equal to empty, then I'll just say continue hallway. And this will be hallway. Otherwise, possible push. All right, so I'm glad that the problem showed up right away. Let's see if this looks better. Okay, so it looks like it's only peeling out the first ones. Okay, so let's now take out the prints. And I'm going to take out these first guys because they're annoying. Where am I printing those? These guys. I don't need those. Okay. Let's try again. It finished and it came up with 44169, which was that it? 44169. Okay, perfect. And it shows the back trace of how to get there, and I don't need that. So I'm going to take that out before I do the test code. So let's comment that, and done. Okay. So now I'm going to put in my real data. And it was DD, CB. I'm just copying it from the line above here. BA and AC. 2 warnings. Just out of curiosity, what are the warnings? Oops. I don't see any warnings. Oh, I'm not using print now. Okay. That's fine. That took 2.5 seconds for the test data. Let's see how long it takes for the real data. It was also 2.5 seconds. Let's see if I got it right. Ah, okay. This is good news. All right, so we finished 22 and 23, which is good. So tomorrow we'll do 24 and 25 because I'm almost at 3 hours streaming, which is a lot more streaming than I normally do. There's a hole, Smab says. Where's my hole? I got a star. Thank you for the star, Smab. All right. Git status, git add source, git commit nation day 23A part 2. Yeah, and then I'll refactor that maybe tomorrow if there's time, because I would like to have it as a proper day 23 with both things at the same time. All right, that was good. Smab says before when it was pulling from the wrong part of the room. Yes, yeah, that was the hole, indeed. Sorry, I missed that comment from earlier. All right, let us, let's see, is there anybody we can raid? Of course, Togglebit's streaming. Let's go raid Togglebit. Oh, Son of Viking's up. Let's go raid Son of Viking. Let me pause my music here so I can hear what he has to say. Son of Viking. Twitch. There we go. I don't know if I have the audio hooked up so you can hear. Oh, I'm watching an ad now. Okay, cool. Oh, he's been streaming for 4 hours. Maybe he'll keep going. I don't know if he's wrapping up or nearly there. But we'll find out. Let's go say hi to him. All right, thank you everybody for watching, and I will be streaming tomorrow with days 24 and 25, hopefully wrapping up Advent of Code, and then getting back to my roguelike. Thanks for hanging out. I hope you have a great rest of your day. Take care.